Hello. So, welcome to the lecture 2. What I have done is on Moodle. I hope everyone is able to access Moodle. Yes. So, Moodle, I'll be putting out slides or at least the lectures for preview for the next few classes so that we can save on time. Right. My request is please do look at the slides and come beforehand. So, we'll be going to be very fast paced as far as some of these applications are concerned. This is just to motivate you towards the project. So the main purpose behind the examples I'll show today are projects basically, right? So okay, so the big picture recap, we talked about the different types of optimization, continuous discrete, a subset being convex for continuous, a subset for discrete being submodel optimization. And then there are some of the other very specialized loss functions which result in interesting convex objectives or convex or discrete objectives. This is just a kind of recap. It's going to be heavily um, centered around projects. So the earlier you latch onto projects, the better. The link was also put out. And you should join. I hope everyone has joined the teams here. Anyone who's not joined teams here? So teams can please do use this code. Small c, small n, small s. Okay. Please join teams. Please ensure you are part of course Moodle. And the other is MS Teams, which has which you can join using the code C, small n, small s, small j, small v, 56. Okay. So as far as the course page is concerned, okay, so there's a playlist of previous offerings, playlist of video lectures, and then there are notes I have also put out. I hope you're able to see all of this. I'll be putting out some more notes, and then after every class, I put out the recording. I record it on Teams along with the slides, and also kind of a small set of notes I put out every class. So this is a course overview. I hope you're able to access this Google Doc. You can also put comments. Kind of, this is our running notes for the class. Helps, right? So you can where I kind of linked to the projects associated with Bharatjan. So by the way, I also put out explicitly the link to the course projects and themes. I hope you're able to access all of this as well. We'll be very soon putting out a link to your project preferences. So we have Suraj. We are introducing different course TAs. So Suraj is also course TA. Suraj. We introduced you to some of the other TAs last time. So we'll have more TAs being introduced every time. I think that's it, Suraj. If anyone wants to reach out, please do reach out. Otherwise, the best place to reach out, everyone, would be Teams or Moodle. Okay, so make sure you're part of both of these. And please do write comments in this Google Doc. Comments or notes. Okay, so Suraj, thanks. Thanks, Suraj, for coming. So Suraj Racha, Priya Mishra, Pratik. So Vedant has been replaced by another TL. But Vedant is also volunteering for this course. As far as projects are concerned, there'll be more students who TA for the project specifically. Okay, so we already had the canonical example from supervised learning, I said in terms of large language models, instruction fine tuning is a place where you need supervised learning. And I gave you an exposure to different kind of supervised learning losses and different kinds of regularizations, right? That was just an exposure. More on that as we delve into algorithms. Again, this is an exposure set of classes. So we finished the supervised learning based on least squares, logistic, support vectors, and so on. We'll quickly do a couple of others today: unsupervised learning and reinforcement learning, etc. So let's look at where unsupervised learning crops up. Pre-training of deep models, right? And of course, I'm not going to give you a tutorial on large language models, but as I had said last time, I'll be putting out these very detailed course notes, detailed notes on large language models. For example, this is a, sorry, I think that is pretty. So this is all about fine tuning. So a lot about transformers. Yeah. So this is about language modeling using RNNs and so on. So I'm sorry, I'm navigating backwards. It starts with this chapter, which I'll kind of allude to today. Okay, so this is the one. Yeah, word embeddings, theoretical and practical insights. This is kind of where I'm going to talk about today a little bit. So I'll make this available maybe in a day or max 2. At least this part I'll make it available today. So this is the unsupervised learning part. Then we'll move towards the other aspect, which is reinforcement learning based on human feedback. Okay. So we already did the fine-tuning aspect through supervised learning. Okay, so there are of course more detailed video lecture on this can be obtained. I have provided a URL where I delve a lot more into the unsupervised learning and representation learning. So let me give you a motivation for unsupervised learning. It's basically autoencoders. That's exactly what I was trying to present here in this chapter, right? Word embeddings and language models. So what are autoencoders? Basically, they are trained to copy input to output, right? And that's what has been a revolution, being able to regenerate data, right? So, and how do you do that? Well, it's possible because you're compressing the original and also learning to reconstruct, right? So there's an encoder which compresses and a decoder that reconstructs. So what is at the core of the heart of this, right? It's basically, this is a simple neural network based autoencoder where you have an input layer, a hidden layer, and a hidden layer, as you can see, creates a more compact representation. And the hidden layer basically is giving you a code to represent the input or output for that matter. The decoder is what produces the reconstruction. The encoder is what helps you encode the input, right? So the loss function is such that you are able to represent. Okay, so there's some problem here, but yeah. The loss function is such that G, so it's correct, yeah. So it's basically saying that G of F. Oh, sorry, there's something missing here. Okay, so we want the original input X. I think the original input is X. That is what got missing here. So X minus G of F of X. Designed so that G of F of X is approximately equal to X. Okay, I'll correct this, right? And why approximate and why not exact?
We could work from a smaller space to bigger space, the data is not.
Right? So there can be a potential loss, and also what we want to avoid is overfitting, right? So so this loss function X is basically, for example, something that measures the distance between the encoded representation through F, decoded back through G, should match the original X, right? And that is the whole idea, right? Learning salient aspects of input and prioritize what to copy and what to not to. right? So you want to avoid overfitting and be able to generalize the generation to other forms of input. And then also what PCA, how many of you have done principal component analysis? So you have done PCA in your basic course, right? We'll have again a very quick brush up of what PCA is and specifically from an optimization perspective. Okay, so this notation X has gone missing in my compilation, but there's an X. So right, what you're trying to do is given an input, encode it. Here's an example where actually used weights. So W1 is the set of weights for encoding, and W1 transpose is what is used to recover. Right, roughly what PCA does is W1 transpose W1 is identity. Right, basically what you want is the hidden layer should be decorrelated. Okay. Now there are some other considerations. So when P, what is P? So P is a hidden layer, right? The dimension of the hidden layer. So you could have this P, right? There's an n dimensional input, so the P dimensional hidden layer, and n dimensional output. So if you have P greater than n, then what would happen? You'll have a lot of redundancy. Your input can get padded with lots of zeros. Somehow the X has got mixing everywhere. The X is input. X can become padded with lots of zeros. So one way is, of course, you can have a denoising autoencoder, corrupt with noise to learn to clean the noise, okay, which we'll not get into. Or the other is insist that both look like Gaussian. Undercomplete is when P is less than n. Okay, so sorry. Yeah, undercomplete is when P is less than n. So let's look at this a little bit more concretely. Let's say we are trying to represent text, and I begin with characters. Let's say 3 characters A, B, and C. What is the best encoding of these characters so that I can predict the next character? Typically, that's what happens when you are trying to autocomplete words. You need a representation at the level of subword units. In this case, extreme case of subword units being characters A, B, and C. So you begin with one hot encoding where you say A is represented by 1, 0, 0, B is 0, 1, 0, and C is 0, 0, 1. Okay. Now imagine 26 characters, you would have a 26 dimensional vector. So that is called one hot encoding. Give a unique key K to each character in the alphanumeric order, and each character is encoded with a vocabulary of with a vector of vocabulary size. 1 is exactly for the kth element and 0 otherwise. Right. So let's say I want to generalize this beyond characters, and I want to look at words, and I want to represent reviews. So review 1 for a movie says, or drama says, the drama was interesting, loved the way each scene was directed, I simply loved everything in the drama. Review 2 says, I had 3 boring hours, very boring to watch. Review 3, I hopefully you don't give this review for the class, but review 3 said, I liked the role that that was assigned to each of the stars. And the fourth one, it's I hate all the dramas of the director. Now look at it, it's a little tricky. This one was an exception, right? So the review 4 is actually quite positive. So review 1, 3, and 4 are positive, but in have different flavors. How do you determine that the sentiment associated in these is positive and the one in review 2 is negative? So now I'm going beyond characters to words. I can say, well, I'll try and have a vector, but what I'm doing is a bag of words representation where I say the word, let's say the one of the sentences which had loved twice, boring once, liked once, and hate 0, entertainment thrice, right? So I think this one, the last one, right? So anyways, collectively across these, you can try and do representation for each of them using a a review in the form of bag of words. Right? Bag of words is similar to one-hot encoding. What you're doing is vocabulary of words. You'll also look at in terms of the frequency of words in the reviews. So use a word frequency in each review instead of just one. Earlier just said one, now we say, well, three. Three times, I will give a count three. So limitation of the bag of word encoding or one-hot encoding is that it's very high dimensional. Right? In real life, your vocabulary will just grow, shoot off very quickly. And the other issue is, of course, each word is being considered as a very independent unit, which is not true. Liked and loved are very strongly related. So that's the motivation, right? So now we want to go beyond either one-hot encoding based representation leading to a bag of word based accumulation through frequencies to something that gives me semantics. So what was the autoencoder basically doing? Well, basically saying if I represent the input in terms of the one-hot encoding of these words, can I, through a neural network, get a compression, a compressed representation, such that liked and loved start becoming or looking similar in the compressed space, right? But I want to do that in a way that is faithful to the original input. That's why I need a decoder, so that I need to train a decoder that helps me ensure the faithfulness to the source. So this is how it began long back. I mean, people use CNNs as well, convolutional neural networks. And there was another motivation. Another motivation was that I should be able to do algebraic operations. So what is algebraic operation? If king is a kind of qualified version of a man and queen is a qualified version of a woman, then king minus man plus woman should be a queen, right? That's algebra we expect. Or if France is to Paris, then Japan is to Tokyo. So so can we get that also through a vectorized representation? So could this be a hypothetical word vector representation now? Instead of a king, a queen, man and woman all being one hot represented, I mean, input could be one hot, but I learn a representation that generalizes beyond the one hot, and the different indices for each of these vectors could semantically correspond to, say, royalty, masculinity, femininity, and age, right? I mean, you typically don't have a very young king or a young queen, right? So age would be something that you might, but on the hand, princess would go low on the age, right? So conceptually, this is what I want. I want some semantics to be also captured in this compressed representation. Is this clear? This motivation? So now if you can try and assess, you'll find that, well, some possibilities exist in terms of being able to recover and apply algebraic rules like king minus man plus woman. You can do that, do these operations to some meaningful effect in this kind of representation. But how do you even get this representation in the first place? That is the question, right? So yes, for queen, you'll need to do subtraction, addition. Where for the other kind of king is to man, then queen is to woman. These are vector differences of pairs, right? Or the Tokyo example, again, you would look at differences of pairs. You may also look at ratios, and ratios make it a little complicated, right? Okay. So going back to the drama example, right? Now, if I had a meaningful representation through word embeddings in low dimension, can I do something meaningful with classification of reviews for a drama? And how do I even learn these representations? So one of the earliest attempts was the so-called continuous bag of words model. I'm giving this example because it's kind of, there's a semblance of PCA, which is easier to analyze, right? So, so what do you do in this continuous bag of word model? You take the sentence, I really like the drama, and you'll take a word window around each word. So drama is one word, right? And I begin with a one-hot representation for drama, right? A long vocabulary list. What would I do? There's no This can't. Okay, so I'll begin with a large vocabulary with one hot representation, and in this case it's drama. So maybe drama is corresponds to some second word. The continuous bag of word model says that I will try and reconstruct this vector using the vectors of all the neighboring words. Okay, so this is I liked blah 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 drama. So I'll vary. So I like the direction in the drama. So maybe instead of vary, I'll just use the word direction, which is indicative of the word drama. So I'll use the contextual representation to recover drama. And what would be the loss? If I'm trying to reconstruct, what would be the loss? Any guesses? Yes. Right. So he's saying that we want some kind of a symbolic representation, and the loss should help you ensure that the symbolic representation for light in the vector space is close to what you recover using the contextual words. So you'll basically use a kind of softmax loss. I mean, loss associated with the softmax function, logistic loss, cross entropy loss. Right. So what you typically do in this case is cross entropy. You look at, you saw cross entropy loss, right? Of the softmax on contextual representation. So you'll take the softmax based on the contextual representation through some neural network and try and match it with the ground truth, which is the word drama. Okay. Fine. So sum on constraint on the sum of So why do you need L2 now? I mean, softmax is basically subject to the constraint that the probability is sum to 1, right? No. Once you decode, so let's say I have these vectors from the neighborhood, from the context. So this may be a 1 here and 0 elsewhere. This is a 0 and 1 in the third location, right? I'll pass this through some neural network. Right? When I pass it through a neural network, I'll basically get probabilities as output. What I have in the ground truth is the exact word, the location of the one hot representation encoding a drama has occurred. So I'll need to compare this one hot representation with a probabilistic vector. That's where I'll have to use softmax, right? So softmax followed by cross entropy loss between the softmax decoding and its corresponding ground truth. Okay, so this is what was one of the preliminary versions of unsupervised learning, right? The word embeddings are being learned through unsupervised learning, where I take for each word in the context, right? This is an input layer. What I was showing on the right hand side on the board is the left hand side here. Okay, so you should be able to draw correspondences. Sometimes in our classes we'll change notations. We'll use X instead of right, small x instead of capital X. You should be robust to all of these notational changes. Sometimes it'll be theta instead of W for parameters. Likewise, you'll find a flipping of position. So what is on the left hand side here is on the right hand side on the board. the input layer, which consists of all these different words with one hot representation. You can see this green is basically the one hot for each of the contextual words. You are passing it through some network, and then look at basically the hidden layer. Finally, at the output layer, you will have again a long vector, the vector of the same size as each of the input words. You can see that each of these has the same size as the output layer, right? C1, C2. But what is missing here is a C0. C0 is basically the word drama, right? This is the word I would have expected to be here. The word drama. That was missing. And I'm trying to predict that this word based on its context. So let's say this is the output sample, which has this one hot representation for drama. I want to make sure that the probability peaks exactly for this word here, right? So in the output layer, how do I force the probability to peak? That's what I was trying to say. You may use the across entropy loss on the softmax. We did that in the last class. So I'll not be repeating what we did in the previous class, right? You remember. You should refer to the slides. It's already on Moodle. So this is exactly where softmax, cross entropy. Why is it bag of words? It's bag of words because you can conveniently interchange. In fact, the models are also trained often by trying and swapping the positions of words. So you want a representation that is agnostic to the sequence. Now, I'm not saying that is where things stop. This was one effort, early effort, right? Look at the notes and of course your projects for more advances. But I hope this gives you an idea of how optimization, these problems are posed as optimization problems, starting with one of the simplest ones. And I also take this example because principal component analysis comes as a very close, well understood mathematical formulation, right? With convergence algorithms, with their convergence properties known. Because unfortunately, a lot of this is engineering, right? There's engineering, you design losses. But is there a counterpart where one can get analytic insights? And that turns out to be principal component analysis. And that's again an instance of unsupervised learning. What happens in PCA is exactly like this, right? You have the X, the input space, a matrix, let's say, and you determine its principal components, and you try and recover X tilde and a recovered version of X, right? And the understanding is that in the process of recovery, you should be as close as possible to X itself. Sorry, just trying to. Yeah, you should be as close as possible to X itself, right? So that's why you say minimize the loss X minus X tilde. The let's say the Euclidean norm, and you may want some additional constraints on U. What would you want U to look like? Any guesses? What should be U? Right. So U needs to capture some of the eigenspace in which the X's multiple instances in there. Maybe there could be just a single X. They exist, right? So this this was interestingly a presentation of PCA in one of the old books. The word encoder decoder dates back to principal component analysis. Okay, so it isn't that encoders and decoders were not talked about then. And as was pointed out, there was some structure expected on U, right? So original is X. As I said, I want to ensure that the compact space in which I learn the representations have some meanings. One aspect of the meaning is that the different components should be as less correlated as possible. You saw the example of king, queen, man, woman, right? We had this age as an implicit factor, right? We tried and learn that. Age could be one dimension. What was the other? Masculinity was one, right? Position could be another. Now, how do you get that? You get that through some structure on the use, and that is where um, the notion of features or these aspects being uncorrelated or less correlated will come in. So that's where the U transpose U structure is there. I'm not getting into more details here. I'm going to share with you a lot more slides which get into the details of PCA. Some of you have already done PCA as part of your basic course, so it doesn't warrant more time. Yeah. Yeah. So I'm talking about PCA here, principal component analysis. In autoencoders, this restriction is not explicitly put. What in many of the modern day autoencoders, first of all, you rely on a lot of data, right? Your data possibly helps you do this decorrelation. There's a lot of engineering also that is used often to kind of, and for example, I may initialize some of these with WordNet. So WordNet gives you structures between the relationship between words. So you can actually enforce that certain words should be uncorrelated. Right. So there's a lot of engineering, initialization, the way these networks are initialized. But let's go back to PCA for now. In PCA, the idea is bring in this uncorrelation by design. Okay. And that is where the U transpose U structure comes in.
Generative models. But when you use the median matrix to transpose in the end to generate the word from it. Right. So why is that a good idea?
So the idea originates. This question is, why do they do that? I mean, not all. Some of the decoders do employ this idea. It's basically motivated by PCA.
Here it is like
Right. I think a lot of it is just hangover of the previous practices. Many of them may not have rationalization beyond some empirical evidence. Okay, so more formally, given unlabeled data x1, x2, xn, xi the feature vectors, what you want to do is for this original representation of of each of the xi's, find a lower dimensional meaningful representation. Right now, if I gave you the elements x1, x2, right, of the vector, and for different data points, I plotted, and if you found that actually they were all along a straight line, what would you do? And especially if they are at this 45-degree angle, what would you do? You would just say, well, pick x1 plus x2 divided by 2. I mean, this is a simple example for everyone, right? This is what you do. All of them are aligned. Why do I need x1 and x2? I just need their average. So this is an example of a lower dimensional meaningful representation, which captures the direction of highest variance. The direction along which the spread is highest is this direction, right? The one highlighted in blue. Okay, so in my optional slides, extra slides I gave, I show the same example in the case of with face features. Let me see if I can pull that up. Okay. Yeah, here. This is a well-known use of PCA using all eigenvectors, eigenfaces, right? So what you're trying to do is capture the directions of the in which the feature spread is highest, right? So variance, directions of highest variance. So you look at these features. If I want to, I really encode faces. What would I look at? I would look at hair region. That stands out, right? Maybe a nose region, maybe neck region. So that's kind of what you do in an unsupervised approach to even segment a face. But capture this across all faces so that I have a good facial recognition system. This was, of course, in the pre-deep learning eras. Or if I had to do the same thing with digits, this is again showing principal component, different principal components, right? Number of principal components. If you capture the original are these 4 8s. Now, if you capture the first principal component, you see you basically getting the outline of 8. But as you go to higher number of principal components, higher which for example, I talked about the average, right? Instead of average, I look at also the second order moments. then I start capturing many of the other finer geometric subtleties associated with the different aids. So this, in some sense, is what is happening with um, PCA. Okay, so that's the goal. So finding a compressor and decompressor such that Xi is close to UVXI. Now, I've already given a hint that the U and a V must have some kind of a relation, right? Transpose relationship. But why is that? I mean, the reason is as follows. If I want to make Xi as close to UVXI, right? If I want the compressor U and the decompressor X to result in good reconstruction of the original data as was shown to this example. So there are some additional properties I would like. So what are the additional properties? Scale preserving. You should have some bounded magnitude. So you are asking this question, why is this practice adopted even today, right? U transpose, VSU transpose. Well, if I had the requirement that the U has bounded magnitude, if, for example, the one norm of every column vector ui is 1, this is an example of bounded magnitude. And if in an expected sense, that's the second property. If xi and xg are uncorrelated, right? For example, if a man and woman are certainly correlated, but let's say a man and a building, that's also some correlation, right? But imagine completely uncorrelated concepts, right? If xi and xg are uncorrelated, then you would like the uxi and uxj to be also uncorrelated in an expected sense, expectation sense. So if I put this constraint, right, again solve another optimization problem, you will find that V will turn out to be U transpose. Okay, so that's the rationalization. These are the two conditions: scale preserving and preserving the uncorrelated nature of inputs in an expected sense. Okay, so it turns out that under these conditions, V must be U transpose, right? So now also additionally, U transpose U should be I. That's a scale thing, right? The first condition was scale, and the second was, well, decorrelated. Okay, so this, I hope this gives you the overall picture of what PCA is doing. And as I said, it's very important to understand how PCA functions, because he pointed out that modern day encoder decoder models also often just latch on some of these concepts without necessarily having the simplicity that PCA was operating in. And it works often, as I said, it does work in practice. So these are the natural constraints. Compressor has US bounded magnitude, and the decorrelated nature is preserved even after the transformation. Okay. So what I've written here in blue is when solved using constraint optimization. So when we talk about Lagrange multipliers later on, you will see how constraints can be injected, right? But you can take it from me for granted that there's a way you can solve this as a constraint optimization problem. Okay. Now, instead of saying I'll put this as a constraint, I've made the job easier today. I said that this is my objective function: minimize xi minus uu transpose xi with a Euclidean norm squared, such with the understanding that uu transpose is I. Right? I could have made this more complex, and I would have said, well, under the previous, right? So the original problem is what? Original problem is minimize with respect to u and v of this objective xi minus uv xi norm square such that u has bounded magnitude, such that if xil xj are uncorrelated, and so on. Right? So I have to put all these constraints. All that reduces to a simpler objective. So also, this is very interesting that there are often multiple equivalent optimization problems. That's also important, right? So should I minimize the case of least squares? Simplest example, right? Let's say I'm trying to fit a regression using a least squares loss. Should I use yi minus w transpose xi square? Should I use yi minus w transpose xi raised to 4, raised to 6? What's your take? You understand the question? Why do we go for squares? Why don't we go for, huh? So there is a property called monotonicity. You can have monotonic transformations of an objective, and instead of minimizing multiple monotonic transformations, you might just minimize a simpler objective. Okay, so there are lots of equivalent formulations. I hope you're getting a flavor of there's no one optimization problem that you may land up solving. You may actually find equivalent forms, which may be sometimes easier. Okay, right, and as I pointed out, there is also still an error, yeah, the one in pink. So my first question was, why should they not be exactly equal? Well, you may want to avoid overfitting, rather make sure that the noise doesn't make your model lose generalization capability. Right, so you want to be robust to noise. Okay, so I'm going to give you a small example. You have to do it as a homework. So it's a simple PCA with X as a random vector and its covariance matrix. So you should analyze what its principal components are. The principal components here will be basically taking the n eigenvalues and their dot product, E1 transpose X, E2 transpose X, En transpose X with the random vector X itself. So, so this is the n principal components. Now the question is, there are two questions here. Find all the principal components of the random vector X equals X1, X2 transpose. Okay, so there are two specific random variables. So these two are basically the general context. Question 1, give Px1 is distributed as per standard normal, which is Gaussian 0, 1, mean 0, variance 1, Px2 with Gaussian mean 0, variance 1, and the covariance of x1, x2 is theta. What are all the principal components of the random vector? Try and study it. And likewise, I make some kind of a transformation. Now, what have I done here? Y is now a vector with a covariance matrix, which is shifted identity matrix, shifted from lambda square I to lambda square I plus alpha square with a matrix of ones, p-dimensional matrix of ones. Right. So the question is, find at least one principal component of Y. Okay. So I'll flash the answer here, but you guys please go and understand this. Okay. So the slides will be available. I'll not spend time on this. Now, having completed the second example, let's go to a third example, which is matrix completion. Closely related. So given observations y1 to yn and the relationship between the y1 to yn is that they're all combinations of some element in X. So what's an example of this? So let's say multiple people here have been purchasing books for reading, right? I hope, I pray everyone still reads books and not, right, only watches videos. So if you're reading books, you may have your preferences. And a Kindle, Amazon, for example, for long used to give recommendations based on your book reading preferences. The genre was being determined internally, right? So now based on that's one certain thing, right? Looking at your preferences in trying and predicting what other book you might be reading, but you're not looking at only your preferences. The model is looking at multiple people's preferences, right? And their implicit features. But what the model is also doing behind the scenes is trying to maximize some profit. That's also important, right? It's not just recommending. So certain books have been hot in the market. There's better return for those books. Right? So what we are trying to do here is the observations y1 to yn are based on a product recommendation matrix, which is X. As I said, the y1 to yn themselves could be interpolations of elements, interpolations through the matrix AJ, right? Could be, as I said, maximizing profit. maximizing, or ensuring that if schools are customers, making sure that schools get recommendations of books which are academic in nature, right? So our goal is basically to try and complete this matrix X. That's our primary goal here. So X itself could have an implicit representation in the form of U and P. Okay? So you think of uh, P as a matrix of product features, number of clicks, number of word occurrences, right? Um, okay, so let me elaborate on this a little bit more. Okay, so you have users and products. So users um, have purchased certain products. This is the matrix X. This is exactly my is given some information, the tick marks, the green tick marks of users who have purchased certain products. I want to guess what the question marks could be, right? The question marks are the unknown entries. Users, as I said, could be people who are interested in reading books, and the products themselves are books. So X is an R M cross N. So there are M users and N products. Now, to fill up the missing entries by for X, what you might want to do is profile the user behavior. So what is U? U is the behavior of the people, which I don't know. Right? P is the behavior of the products, which I don't know. What I have access is to the information of which user is buying which book. Certain users might be more sci-fi driven, certain users might be more comedy, action, and so on, right? So there could be profiles. I want to discover those implicitly, and that's what you would do, right? I mean, if I were to look at the book reading patterns of people, I would implicitly try and guess. This you want to do it based on data here.
Is the matrix of product feature. Is that known beforehand? Like, for example, if I would go for the number of pages,
so the question is, would P not be uh, framework, right? Point is, at some important milestone in the trajectory, you would be looking at this problem, exactly like PCA. Right? And why did we keep the U and U and V to be orthogonal? Why? Because there was some motivation for keeping decorrelation. Right? So likewise, this is a canonical example. Now, you can see this uh, the matrix here, right? So what you're trying to do is profile the U transpose, which will look like a column. So in fact, for each user, you will have such a column. This, what we are showing here is U transpose P for one user and one product. I mean, basically having one feature for each user. So if you were to do this, you'll basically get a rank one matrix. Rank one matrix is obtained through multiplication of a column with a row, right? But now imagine doing this with multiple other features. So I've taken a very simple example where each user here, so user is blue, green. I'm saying each user has exactly one feature. Each product has exactly one feature, right? the simplest case. So if imagine the only feature for users were age, right? He said, no, there are a lot of complex information, but I'm going to simplify. I say every product had only one feature, which is number of pages, right? So number of page. So imagine I had a silly model which said, sell the book proportional to the age of that person. You laugh off at such a recommendation system, but I'm saying that's the simplest version, right? If I had no complex, no understanding of the complexity, I would come up with some simple idea, right? So think of this as right, this vector as the age representation for the users, right? And think of this another vector as the number of pages in the book. And what you'd come up with this is a very silly approximation to X, because that's not a reality. I don't purchase books based on the number of pages correlated with my age, right? Yeah, let's not get into attention and let's stick to this problem now, right? So now you understand. Now imagine if so this is when k is 1, right? You understand this is k is 1 means there's exactly one implicit feature, which is age and number of pages. But imagine now I want to make sure that the k is non-trivial. Obviously, book doesn't have just pages; it has many other features, and you all are your entity is beyond just age, right? So I want something, some value of k which is greater. Let's say could be greater than equal to the rank, right? Rank of um, x. In other words, what you're trying to say is, well, can I come up with U transpose P representation such that I'm able to compress the information in k dimensions, non-trivial k dimensions, such that I can recover my x as faithfully as possible. Okay, let's try and write down the optimization problem. Find the simplest matrix X such that AJX is as close to YJ, the observations, as possible. I'm trying to record the class. Yeah. So what you see here is very much in the spirit of our previous example of PCA. I'm trying to come up with some represent small rank decomposition possible. One way we can do that is, as I said, decompose X to be U V transpose. What I've done additionally is added a sigma at the middle, which is for scaling, right? So sigma is a M cross N rectangular diagonal matrix. It turns out that the under certain conditions of the objective, the diagonal elements of sigma have some meaning, singular value, and so on, right? But for the time being, this decomposition will ensure that we have a small rank representation, right? Lower dimensional representation of X. Now, what you see on the right hand side, and here's a simple example I've taken. Let's say I have X is only 3 elements. Okay, so X, let's say, has only 4 elements, but it's a symmetric matrix, so I consider only 3 elements. So I have considered x1, 2 and x2, 1 to be the same. So x12 equals x21. Okay, so if I were to plot rank, okay, as a function of these three, so imagine, right, I have x22. Oh, so I have actually dropped even x11, but yeah, I can do it in a 4-dimensional space. But let's say this is 1. Yeah, I kept this to be 1 for simplicity case, and this is x12, which is x21. How do you think the plot would look like as I change x1, x12, which is x21, and x22 for this matrix? How do you think the rank will look like? Sorry, x minus y square. So it's not good. So I hope you got a hint here, right? It's not going to be as smooth as that, right? You see, this rank has a lot of kinks. No, unfortunately, no. Right. So see, rank is basically what is going to be, huh? Yeah, it will be discrete, right? So it might look something like this gray curve. What we want is the simplicity captured through a good surrogate to rank, a good approximation to rank. And it turns out that the so-called nuclear norm, which comes from the sigmas of this representation, this nuclear norm x, so we have not talked about nuclear norm, but here our exposure to nuclear norm, this is kind of the envelope of the rank function. You see the orange curve? So if the rank were to look like this, then our envelope might look something like this, right? And why is this interesting? Well, this is interesting because, as I said, simplicity needs to be also materialized. Yeah? You want to solve that objective function. Okay. So, as I said, a lot of optimization is also about convenience. What is the objective that is amenable to a solution in terms of maximization or minimization? In this case, minimization. Right? So, yeah, a little bit more on this, right? So, singular value decomposition, what happens is you have x as u sigma v transpose, with the understanding that v transpose v is I and u transpose u is I. This is singular value decomposition, which you probably know from your basic linear algebra course, right? And the sigma has the singular values, sigma 1, sigma 2, sigma k. And the rank k of x will be less than equal to the min of the 2 dimensions, m and n, by virtue of this decomposition itself. Now, what exactly are these? So, what is the connection, by the way, between eigenvalues and singular values? We have also tried to show here. So, Ax is lambda x will mean that lambda is the eigenvalue, right? So, you can write A capital X, it's a stack of all eigenvectors of x, as x lambda, which is the diagonal matrix of all eigenvalues. So, the relationship is also being shown here. If you consider x transpose x, it can be written as u sigma square u transpose. Right? And if you write x transpose, it's v again, you know, sigma transpose v transpose. So, so what is basically happening that the eigenvalues of x transposes and x transpose are the squares of singular values of x. So if x is a matrix and I say it has certain singular values sigma, then its eigenvalues are the eigenvalues of x transpose x turns out to be the squares of the singular values of x. So eigenvalues and singular values may coincide, but they may not. They are, right? It's not necessary that they'll coincide. So if x is n real n cross n real symmetric matrix and non-negative eigenvalues, only then it coincides. Otherwise, the genesis is slightly different. Right? Singular eigenvalues is using this, ax is lambda x, whereas singular values are in terms of the singular value decomposition, which result in the eigenvalue decomposition of x transpose x. Is this clear? So the difference between singular values and eigenvalues. Again, as I said, this is going to be a little fast-paced course, so you'll have to do some reading up or ask questions if you want. Okay, so now coming back to the nuclear norm, right? We want simplicity in the matrix X. So, if I consider X to be a scalar, there's a simple example. If instead of all of this, if X were a simple scalar, right? If I had only X11 and it's this is X11, and I was to look at rank, right? I mean, what does rank basically mean? You can see that rank of X is 1 everywhere except where X is 0, and again 1 everywhere, right? Because Y is rank. And now, if you look at the nuclear norm of X for this case, the nuclear norm, okay, it turns out to be the sum of all its singular values. Sum of all its singular values is basically the absolute value of X. There's only one singular value X. It's basically absolute value. Okay, so I'll use a blue chalk for me. Is this clear? So, I mean, just showing that it's indeed an envelope, the simplest case. So imagine extrapolating from here, from the case of a scalar X to a two-dimensional matrix X, and so on, right? So nuclear norm is giving you this envelope. So rank function is not continuous, but nuclear norm is continuous. It turns out to have also a nice property called convexity. Okay, so we'll talk about convexity, but it's another one of those properties which gives you a powerful way of analyzing functions, algorithms, convergence, and so on. And then it gets applied even in cases, the algorithms with their analysis and motivation for the analysis based on certain interventions in the algorithms, they get applied also when convexity doesn't is not guaranteed, right? So this is another nice property. Nuclear norm is continuous and also convex. The other third property, why do we look at this kind of envelope, right? They have the same minimizer. Okay, so that's important. The minimum for the nuclear norm and the minimum for the rank function, they coincide. That's why I call it envelope. Okay. In fact, it is, when we say envelope, it is not just coinciding by a minimum, but the tightest surrogate. It's actually tight. You can't get tighter than that. That's why it's called an envelope. Right? It's just like you have an envelope wrapping. It's basically the tightest kind of container for the object. So they have the same global minimizer. Is this clear? So with this understanding, right? Again, we go back to our objective. Yeah. This is true for Rn. So I'm able to illustrate in for n equals 1. You possibly can do this, simulate this and show it for two-dimensional, I mean this matrix as well. Okay. Okay, so now is our optimization problem. I want to make sure that my observations Yj is based on attempted completion for the matrix X through a projection Xj match as good as possible, right? This is like the PCA thing. Only difference is as I complete X, I'm projecting it through some operation Aj. Operation, as I said, could give me the sales of books, right? So I want to match the actual sales of books or satisfaction of users as well as possible, or even the clicks that the user actually purchased a book, but with a simplification, which is that I want a simple X. A simple X is in terms of rank constraint X, and that is through the nuclear norm, right? So what is X star? It is X star is sum over the indices I. Indices I which range the minimum of the 2 dimensions of X, the minimum number of users and the number of books, right? And it's a summation of all those sigma I singular values of X, right? And the singular values of X come from the singular matrix, the diagonal matrix of singular values, U sigma V transpose, right? U sigma V transpose, this corresponding sigma is what gives you the summation of the sigmas gives you this envelope as well. Is the story clear now? It's on the board and also on the slides. Yeah. You want to add? You're saying there could be alternative optimization problems. His proposal is why not have K as a hyperparameter, right? But then you'll have to. Point is, you need some other data to give you that value of hyperparameter. The more you are deferring your optimization to tertiary input, the more you're moving away from optimization itself. You can do that. You can do a grid search on K on some validation data. And I'm not saying that doesn't get done. That sometimes that's also useful. But yes, in fact, even here, right, I can say it's not free from hyperparameters. What's the hyperparameter here? I've not written it, but there's a hyperparameter I'm using even here. Yes. The hyperparameter is 1. What is a hyperparameter? Yeah, right. So this is this hyperparameter, which is basically multiplication. There's a multiplication, right? The weightage for this is called the scaling weightage hyperparameter. Okay. Now question is, how do you solve this? We have come to this. Can I use PCA solution here? A PCA can be solved quite efficiently, right? So it looks like it turns out that yes, as a PCA kind of algorithm can be used to solve this also. But the only thing is, you will have to use PCA iteratively, not once. Why? Exactly. I mean, we said, we could have done a grid search on K. Instead of that, we are now doing iterative PCA. Why iterative? Because you have to threshold based on sigma, so on the nuclear norm. Okay. So what does the algorithm look like? Sorry, I'll just. So this iterative singular value thresholding, that is the name of the algorithm. Iterative singular value thresholding. What does it do? Okay, so I'm giving you a basic idea here. So let's say I don't use X star, which is the nuclear norm. Let's say I didn't have nuclear norm. I solved this objective first. That is the first component. Solution to the argument of yj minus aj x summed over all the all the i's. So all the j's. That gives me an x naught. Then what I do is I sort all the singular values, sigma 1, sigma 2 of this x naught. Okay, and then what I do is I keep including those sigma i's till the objective decreases. This objective. Basically, that was the whole idea, right? I didn't want all. If I actually picked all the dimensions, I won't get a simple enough x. So this is telling you, well, sort by the singular values, sigma 1 to sigma n, and keep including them to generate. Now, every time you include a sigma I, basically now your sigma naught has become low dimensional. And generate your x naught till the objective keeps decreasing. This objective keeps decreasing, right? So by including only the first I singular values, like you're giving and going until I, right? And first I singular values, you are basically getting a simplified x tilde I equals ui sigma I vi, where sigma I, capital sigma I, has only the first I singular values. Okay, it turns out to be the algorithm. I mean, looks intuitive, but we will, of course won't get into any convergence properties. But this is an algorithm which works well to solve this objective, right? So there are other ways. As you said, there could be multiple ways. Another way of solving this is by assuming that X is a another kind of low rank decomposition, LR decomposition. Again, you have done an LR decomposition in your linear algebra course, right? So again, math you'll have to brush up. I have on the um, Moodle page, I have also there's a book on linear algebra. I think can't find it. I have posted it somewhere. The slip sheets, but there's a book on linear algebra as well. So please do brush up if required. Okay, so you can also do a LR decomposition and optimize for L and R. Now this brings up another kind of new names come up, right? So far we are talking about matrix completion, but moment you bring LR decomposition, you have another interesting area called non-negative matrix factorization, NMF factorization. Again, for those of you who start reading papers, you'll find these terms coming up. So what is this doing? Is basically saying, well, I'll have L as like U transpose and R as P. You remember the U and P? We went one step ahead and brought in the simplicity of X through the sigma. But imagine I stayed in the U and P space. Then what you want to do here is minimize the usual objective plus bring in some norm penalty on L and R. Okay, that's one way of another way of actually also imposing simplicity on the solution. Or you may say, well, rank of each is less than equal to k. So a whole bunch of solutions can exist, right? So this brings us explicitly to the next application, which is the low rank and non-negative matrix factorization. Now, why is non-negativity required? Okay, let's go back to the same example. Why is so non-negative matrix factorization? So we didn't have non-negativity on the U sigma V, right? When we considered X to be U sigma V, did we require any non-negativity? No. But if I had a different representation, okay, so here's my different representation, which is and you remember one motivation for L was user and R was product features, right? So it's possible that I might want the users and products to be represented using features that are interpretable. And the interpretable representation could mean that you want non-negativity. I mean, what does it mean to have negativity in age, right? Doesn't make sense. Or academic profile, there's nothing like negative. You either have 0 or you have some academic profile. So if you want one form of interpretability is putting non-negativity and make each element of P and U positive. So that you see, that's another kind of constraint. Okay, so so that while this stemmed from the previous example, this non-negative matrix factorization and low rank factorization is itself also a very interesting area, right? So find matrices LR. Again, L is M cross K, R is K cross N, taking Q from the same, right? M users and N books example, such that AJ, this kind of composition on AJ, matches the YJs as well as possible. So that by virtue of this, AX has low rank, right? So you might recall that I've also put a link to the Collab notebook here. So even in the case of regression, right, we wanted the weights to be positive. Okay, let me just. bring up this collab notebook. So this taking some time. Yeah. So it's possible that if in regression we want the weights to be positive, what we may do, some of the weights in regression could be, for example, the weight of the weightage that should be given to uh, a person's previous job experience or previous pay as for the pay that is being offered in a new company, right? The companies do that often. So you want some kind of positivity. So there's something called projected gradient descent. So if you look at the collab notebook, you'll find that there's one way of getting the new set of weights, W new, B new, is doing a gradient descent of the old weights and doing a plus. This plus thing, right, is basically saying I project, which means if the weight turns out to be negative, clip it to 0 or push it to 0. I just try and bring up the collab notebook. Okay, but anyways, you can. It's not coming up for some reason, but the link is accessible. You can try and go over it. Okay, so the matrix factorization problem is this, and with this, if I have this low rank, there's no need for matrix regularization explicitly, right? Because L itself is of m cross k dimension. So what will happen by virtue of k? The rank of LR can never exceed. You understand, right? If I have X to be a column times a row, the rank of X will be 1. So if I take X to be having K columns multiplied by K row matrix, then rank of X will be less than equal to K. So this is a kind of regularization, but on top of that, we want non-negativity constraints. So you want L and R, like the product features, the user features, to be also positive, right? How do you think you'll solve this problem? So I give you a hint that in the case of linear regression, you could just clip the weights. What do you think will happen here? Similar clipping, but you need an iterative algorithm for that, right? So this clipping is called projection. Do this and add projection step to LNR. Project back. Every time you solve it, if you find some of the weights of L are negative, push it back to 0. I think this looks so heuristic, right? Is there some principle governing this? Well, it turns out that projection is not that much of a black art. There is some very interesting, there's some properties that projection preserves under, of course, convexity assumptions. Okay, so projection is good. It's helpful, and the projection step is much neater, and it actually results from some nice rescaling and has connection with the constraint optimization. The Karsh-Kuntakar conditions that we'll talk about later on have connections here. Okay. Okay, so this is the new algorithm. This is my revised algorithm for the same kind of matrix completion problem, but now viewed as a non-negative matrix factorization problem. You will iteratively project the L naught and R naught, right? So this is the projection step. Looks a little messy. All we are doing in this messy step is basically saying, if you're less than 0, make it 0. That's all. Okay. So this is called projected. It's an special, case of something called proximal gradient descent. Okay, so this is iterative singular value thresholding. We could also have nuclear norm for L and R, right? So that's another thing. You say, I don't want L and R to be just n cross k and k. I want them to be also low rank. You put a nuclear norm. Now you can see, you can create your own bhelpuris, right? You can say, well, I have these different elements, put them together, create new recipes. Okay. So sometimes what happens is y is fully observed. So in which case, we want a non-negative low rank factorization of y approximately equal to LR itself, right? A is not being there. You have y itself as fully observed. So then the problem basically becomes y minus LR. So, right. So as I said, A becomes your identity matrix. And this is what you typically are doing. Typically what you're talking about is just complete my matrix. I'm not looking at any composition on top of the matrix itself. Right. Okay. So I'll just give you this last food for thought. Clustering. Now we are moving. We already have started moving from continuous to discrete optimization. Okay. But more explicitly, there's also unsupervised learning where given unsupervised data, the feature vectors xi, what you're trying to do, for example, is find membership of points, the different points, which clusters they belong to, while also trying and determining the clusters themselves. So two problems exist, right? I want to find the clusters and I want to know which are the points that belong to those clusters. I want to find cluster centroids, cluster representatives, and membership of points to those cluster representatives. So one way I can pose this problem is saying, oh, okay, so again, xi got missed here for some reason, but yeah, let's say I want Pij to Pij is the membership of each point to one of the clusters, and the cumulative. Okay, I think this is mood. That's it. Okay, what has happened? This is mood. Yeah, yeah. So I want the Pij times xj to be contributing to the closest mean. Pij should be such that a point j is ascribed to the closest representative vector mu I. So I want to minimize over the Pijs, but are the mui's themselves known? So I want to leave you with this food for thought. We are already supposed to conclude. How do I now solve for two unknowns at a time? Mui's and the Pijs, right? If I knew the mui's, it looks simpler. I mean, then I can just greedily assign. But the challenge is I need both of them. And think of the different ways you can solve. So I'm happy that the class is coming out with alternatives. Always think of alternatives. There's no necessarily one way to solve the problem, right? So should the mui's themselves make sense? Should they be means? Should they be medioid or centroids? Should they correspond to some actual physical points, right? If I say, create facilities, so I'll leave you with this last problem, right? If I imagine that these points are cities, and I want to create facilities in the form of, say, warehouses, from where supplies can be made to the different cities. Now, it's possible that I do clustering based on demand, and one mean turns out to be in the middle of Narmada River. Another mean turns out to be in the middle of Godavari River, right? Do you think it's feasible to construct a warehouse there, right? So means have a limitation, right? Because they'll just land up, you may have a no man's land where the mean, so you may put constraints. You say, oh, no. I want to make sure the mean is actually in some city, one of the livable cities, right? It's on land. So constraints make clustering a lot more interesting, a lot more richer. Right? There's many variants to this problem. So think about it. Again, I'll conclude, mostly be concluding the discrete optimization in the next applications next class, and then we'll move on to the basics of optimization algorithms. Okay. So please do brush up. I'll be on Moodle. I'll post the slides so that you are ready for next class as well. Thank you.